data centers consume a large amount of energy. This leads to several problems, both from an environmental and an economic perspective. The rise in energy costs in recent years, together with international regulations aimed at reducing energy impact, have pushed data center operators to implement solutions for optimizing energy use within their infrastructures. This lesson will explore the main state-of-the-art techniques for optimizing the energy consumption of data centers. We will analyze the possible interventions by distinguishing three main areas of action: the cooling system, the hardware, meaning the physical devices dedicated to processing and storage, and the network, that is, the data communication infrastructures inside and outside the data center. To ensure reliable operation, the servers and other equipment in a data center must function within a well-defined temperature range. However, during computational activity, they generate a significant amount of heat. As a result, cooling systems play an essential role in maintaining stable operating conditions, preventing overheating, hardware failures, and potential service interruptions. Cooling accounts for 50% of a data center's energy consumption. This value has a significant impact on power usage effectiveness, which is the most commonly used metric to calculate the energy efficiency of a data center. The efficiency of cooling systems can be improved through dynamic energy management techniques that adjust server operation based on workload. This approach makes it possible to turn off or put idle servers into low power mode, reducing heat generation and, as a result, the need for cooling. Another way to reduce energy consumption related to cooling is to utilize advanced and highly efficient cooling technologies, especially in buildings and data centers. Among these is free cooling, which uses outside air to cool the internal spaces of data centers. This technique has led to a concentration of data centers in the coldest areas of the planet. For example, Meta's data center in Luleå, in northern Sweden, makes extensive use of free cooling thanks to the favorable climate conditions. Liquid cooling uses water or other fluids to absorb the heat generated by servers. Hot aisle, cold aisle containment is a passive cooling strategy that separates the hot air expelled from the servers from the cold air used to cool them. The cabinets and racks in data centers are arranged in alternating rows of hot and cold aisles. The hot aisles face the air outlets of the servers, while the cold aisles face the air conditioners. Artificial intelligence technology enables the predictive and adaptive control of advanced cooling systems. The use of machine learning algorithms makes it possible to process real-time data on temperature, humidity, and thermal load, dynamically optimizing the settings of cooling systems. For example, the groundbreaking joint project, carried out in partnership between DeepMind and Google, led to a noteworthy 40% reduction in energy costs related to cooling servers. The residual heat produced by IT equipment can be effectively recovered and reused for heating buildings, producing domestic hot water, or as a source of thermal energy in industrial processes. This strategy makes it possible to reduce energy waste and significantly increase the overall efficiency of the data center system. A concrete example is the Lefdal Mine data center in Norway, which uses a liquid cooling system based on the use of naturally available cold water in the area. The center plans to reuse the heated water resulting from the cooling processes by transferring it to external infrastructures, including a coastal fish farm, thus contributing to an industrial symbiosis focused on sustainability. The hardware, which includes among its components the servers used for application computing and the storage systems, accounts for about 26% of the energy consumption. The adoption of high-efficiency hardware is one of the most effective measures to reduce the total energy consumption of data centers. Improving the operational efficiency of physical components not only lowers energy costs, but also reduces heat production and, as a result, the load on cooling systems. The technological choices underlying the installed hardware play a strategic role. A first strategic measure to improve the energy efficiency of a data center concerns the selection of high-efficiency servers and storage systems. The energy performance of hardware depends on multiple factors, including the age of the devices, internal architecture, and the quality of the design. The use of certified equipment, such as those compliant with the Energy Star standard or equivalent, makes it possible to select solutions characterized by an optimal balance between performance and energy consumption. These devices undergo rigorous efficiency testing that ensures significantly lower consumption compared to their non-certified counterparts. In particular, some models of certified servers can offer energy savings of up to 30%, helping to reduce operating costs and the overall impact of the infrastructure. An increasingly important trend for making hardware more efficient, both in terms of energy and beyond, is the adoption of modular hardware systems, that is, a highly flexible and scalable approach to building and managing physical infrastructure. Unlike traditional data centers, these systems do not require high initial investments or long-term planning. Instead, they allow for incremental growth and ongoing customization of resources. Modular systems are made up of interchangeable modules, such as servers, storage units, and network devices, designed to integrate with each other and operate efficiently. A key role in the development and adoption of these systems is played by the Open Compute Project, an organization that collaborates with more than 400 companies in the industry to share guidelines for data center design. Sustainability is a fundamental aspect in the development of modular hardware systems, which incorporate innovative cooling and energy management technologies into modular systems, reducing both energy consumption and operational costs. Another approach that affects the energy efficiency of a data center concerns the way servers are distributed within it. A high-density data center is a facility that concentrates a large amount of computing power in a small space. This leads to improved energy efficiency per square meter and optimizes the distribution of power and ventilation. Another aspect to consider, especially when large amounts of data need to travel in and out of the data center, is related to network devices. The internal network infrastructures of data centers can be optimized to reduce the energy consumption associated with data transfer. Among the main techniques we can mention: efficient data movement to reduce the distance traveled and the number of switches crossed, the use of highly efficient network hardware and dynamic management of network bandwidth, and the optimization of information flows to minimize network device activity during periods of low load. In the case of data that must travel outside the data center, placing data centers close to users or major data exchange points reduces latency and the amount of transmission required, resulting in lower network-related energy consumption. This strategy has a direct impact on reducing energy consumption in data communications. The energy efficiency of data centers is the result of an integrated approach that involves hardware architectures, thermal management, and optimization of data flows. Through the combined adoption of cutting-edge technologies and intelligent management strategies, it is possible to significantly reduce energy consumption while ensuring reliability, scalability, and high performance. The continuous improvement of these systems represents a strategic priority for the sustainable evolution of digital infrastructure.